This lesson is over constant acceleration, which we also call kinematics. So we can also write this. And what we're talking about here is not objects that are moving at constant velocity. That was a previous lesson. Constant velocity means that it's just going at the same speed. In this one, we're talking about accelerating objects. So what acceleration means is that there is a change in your velocity, and it's specifically defined as the rate of change. So that definition is written as an equation here. It's your change in velocity, the delta, this is called delta, means a change in, we have velocity over a change in time. Now, velocity means two things. It's your speed. I'll write this over here. Velocity is not only speed, but it is also direction. So, what are ways that your speed can change? You can be speeding up. You can be slowing down. And that's basically what can happen to your speed. And so most of our problems are going to be focused on these two especially. Our problems are going to show objects that are speeding up and objects that are slowing down. That's basically it. Another way to change velocity would be to change direction, which we are not focusing too much on today. But there you have it. So clearly we have some equations in front of us. Uh, we use these three equations kind of together when we solve problems. Sometimes we'll use the first equation, which I call equation 1. I call this one equation 2 and equation 3. Just makes sense. Sometimes we'll use 2 by itself. Sometimes we'll use 1 and 2. Sometimes we'll use 3 by itself. And there's all kinds of combinations we can do with these. So let's define the variables. If you saw the lesson on constant velocity, we know a couple of these. This is the position at time 0, which is often going to be 0. This is a position at a later time, which is in meters. So I'm going to put this here, if not stated otherwise. X naught will be equal to 0. So if we say the starting position is 2 or something like that, then, well, it's 2. But if we don't say it, we'll just make it 0. It just makes it easy. And that's the only variable you can do that for. You cannot do that for other ones. You cannot just say something else is 0 because it wasn't stated. So that one's very special. Okay, we call this V naught. This one here is called V naught, or students mostly call it V0 because that's what it looks like. This is the velocity at time 0. The units for velocity, meters per second. This is the velocity at a later time. A is our constant acceleration, which I had not mentioned. So the objects that we are looking at, the problems that we can use these equations for, they must have a constant acceleration. And the units for these are, in truth, they are meters per second per second. But most physicists will write meters per second squared, which is mathematically equivalent to meters per second per second. So even though that's the one I just erased is what it really is, we will always see it this other way. And so we'll just get used to this way of writing it. Maybe in this lesson or in a later lesson, I'll explain the meaning of meters per second per second. But We'll see if we get to that point there. Okay, and of course t is time. At this point I usually say it's best to just get started with an example. We're going to skip example 1. I think example 2 makes a little bit more sense to understanding what is happening here. So before we even read the problem, we should always make a list for these types of problems, and you should make the list in this order. So we have x naught x, v naught v, a t. We'll read the problem. Allyson Felix, an Olympic runner, accelerates from rest to 10 meters per second by the end of her race. Her acceleration is 2 meters per second squared. The question for part A is how much time did it take her to reach the final velocity? So, let's write that these are equal to something. They give us some numbers clearly. They don't give us time. We're going to solve for time. That would have been the easiest one to put there. But here, this one is pretty explicit. It's pretty obvious that that's meters per second squared. I'm sorry, it's pretty obvious that it's acceleration. Another way of knowing its acceleration is because of the units meters per second squared, which if you go back to this page, they are the only, acceleration is the only one with those units. So it must go there. So the rest of this, let's try to figure this out. So Allyson Felix accelerates from rest. A couple of lessons ago, we explained what rest means. It means that you are not moving, which makes sense in a race. They start you at 0 speed. And so our velocity at time 0, v naught, should be 0. And this is because it starts, I'm going to write it over here. It starts from rest. What I'm showing you here is how we get these numbers, because it's not obvious looking at that word rest that a 0 should go there unless you understand it. So you go from rest to this speed. Makes sense for a runner. So our final velocity, or our velocity at a later time, would be 10 meters per second. And that one's a bit more explicit. So it starts from here, v naught, and it gets to that speed, which is v. Okay. Have we done everything? Almost. If not stated otherwise, x naught is going to be 0. So go to here at x naught, that's 0. Cool. We are missing t and we are missing x in this list of variables, which of course is what they're asking us for. What distance x and what time t. So how do you solve for these using those equations? They look intimidating. It's actually very simple. And with practice, you'll gain some confidence in this, but practice is critical. We need an equation with t. So let's take a look. You can pause the video if you want and look for yourself. But there's a t here, so that's an equation, and there's a t here, which also is there. The only one without t is the third one, so we're going to forget about the third one for now. It's going to be either equation 1 or equation 2. Let's go back. We are missing x. And so in algebra, you want the t in your equation because that's what you're solving for. But because we're missing x, you don't want it in the equation because you can't deal with two unknowns most of the time. So we want an equation that does not have x, and so that's only going to be the first one. This one does not have x, the first equation. So we go here. V is equal to v naught plus at. We will use our same method of substitution. Starting at the left, we'll put in, for v, that's a 10. V naught is 0, so I just like to cross it out and say that that's 0. and I don't bother putting it down here like that, we don't need to. We're just going to keep going. Forget about the plus because there's nothing to add to it. It's just going to be a times t is the relationship there. So a times t means we're going to put this in parentheses. That's 2, and I'm sorry, that's just t. There's no number to put because we don't know what it is. So to solve this, we just divide by 2. Just divide by 2, sorry. Let me write that a little bit better, which comes out to 5 seconds, just like that. It's at this time that I like to point out we figured out the answer. We'll talk about the meaning of all this. Um, Sometimes I'll give you points for parts of the list. For example, I might give you a point for knowing that rest means v naught is 0, or rest, okay, rest does not mean v naught is 0. Rest means that it's not moving, and since it starts from not moving, from rest, that means v naught is 0. So I'll give you a point there. Sometimes I'll decide to give you a point for other things in this list as well, sometimes. I'll give you a point for using an equation to solve for t. I'll give you a point for substituting your numbers correctly. For example, v is 10 and a is 2. So I'll give you a point there. Point for a correct answer. That means you put in your calculator correctly or just divided it correctly in this case. And then a point for units, which I'll usually write off to the side and give you a point for that. So if I go in and count all these points, that's 1, 2, 3, 4, 5. If that's all I was looking for in this quiz, that would be a 5 out of 5. That would be a 100. But let's keep going. So I want to show you all the meaning of acceleration. I'm just going to take a moment here. It says that Alice and Felix's acceleration is 2 meters per second squared. Okay, and think about a race, right? So she's starting at position 0. And here's the meaning of acceleration of 2 meters per second, or just acceleration in general. What this number actually means is her speed will increase by 2 meters per second every second that passes. Remember that these units are equivalent, but the way they're written here on this side make a lot more sense in a way. So after a second that she's been running, let's say she's here. Actually, let's say she's a little bit closer. After a second, she's right here. She should be going 2 meters per second after 1 second. After another second, she might be right here. So that was 2 seconds total. Well, her acceleration is saying that every second that passes, she will gain 2 meters per second of speed. So she should be going 4 meters per second now. And I don't have enough space here to accurately show where she would be after 3 seconds because she's getting faster and faster. But according to the acceleration, she is getting 2 meters per second faster, 6. And after 4 seconds, you get the idea. This is 8 meters per second. And then finally, after 5 seconds, it is 10 meters per second of speed. That is the meaning of acceleration. Every second that passes, she will get faster by whatever this amount is, okay? All right, let's finish up the problem. What distance did Allison cover in this time? You don't have to write the list again. We know what t is, it's 5 seconds. Now, by the way, I grade all the work over here where you showed the work. You can write the 5 seconds here, but I will not grade it there typically. I'm typically looking for starting numbers, not ending numbers. Numbers you start off with, not like calculations. So you can put it there if you want to. We need an equation now for x. And once you know all the numbers, you can use any equation you want. We're clearly not going to use the first one. We already used it. It would be useless to use it again. And most people agree that the best one to solve for x is the middle equation, which I will write for us here. So we'll write x equals x naught plus v naught t plus 1/2 times a times t squared. Again, looks intimidating, but it's actually very simple. We'll make the list visible here in the video. We don't know x, so we write x. X naught is 0. V naught is 0. So I'm going to cross out the whole thing because V naught is 0. I'm going to write this on the side. If V naught is 0, and no matter what t is, it doesn't matter, 0 times t will still equal 0. So the whole thing is just 0. I know that it's 5 seconds, but let's put 5 in there and see what happens. That's still 0. So we don't write the 5 down here. It's 0. It's gone. So this is a really easy equation now. This is 1/2 times the acceleration times time squared. The acceleration was 2, and the time was 5. Take some time to type this in your calculator, see what it is, or you can do this mentally. 1/2 times 2 is 1, and 5 squared would be 25. So that's how far she went. And that's why I couldn't really show it too well over here because just wasn't enough space to show it accurately. Okay, I'm gonna erase all this. We don't need all that. So that problem is done. And I would score it in a similar way. I would give you probably points for having an equation to solve for x, an equation for correctly, a point for correctly giving the answer. And I usually don't give double points on units, but this unit point up here would probably include this one that was there. So that would have to be correct to get this point up here. So that's just an example of how many points I would give, or how I would score it. I'd like to just quickly solve example number 1. Feel free to pause the video at any time, take a break. We'll start with the list. It says a car accelerates from 13 meters per second to 26.8 meters per second. Very clearly stating what's happening. It's going from this speed or velocity to this one, but since we start with that one, we call that v naught. So that's 13 meters per second to 26.8 meters per second. They give us explicitly the acceleration. So we'll put that there. And they ask for how far did the car travel in this time. What they want to know is x. They did not explicitly state x naught, so we will put a 0 there. Now, truth be told, you can solve this 2 ways. You can solve first for time, and then, in other words, what I'm saying is you can solve for time using the first equation, which is very easy, and then you can use the second equation, which solves for x directly. But in this video, I want to give you a chance to use the third equation. And so this will be our practice for it. We shouldn't be scared. We shouldn't be afraid of that third equation. Oftentimes, it's very useful, and it's very fast to use sometimes. And so we're trying to solve for x in this equation, but trust me, it's not so bad. Let's start by substituting. We have 26.8. Don't forget the squared. V naught, we're going to substitute, is 13 squared plus 2 times 2.2. And here we're going to be very clever about how we do this. X is unknown, so we're going to leave it as x. Okay. X naught is 0, so I'm going to cross it out. what is x minus 0? What is anything minus 0? Well, it's that anything. It's whatever that is, right? So just leave it as x, and that's the way I've written it here is already done. This may not look easy, but we're going to simplify some of these things. We're going to take 26.8 and square it. That gives us a number, 718.24. And you should be trying this out, by the way, doing these calculations on your own while you're watching this, just to get that muscle memory, just to get that experience, that practice, doing all these little things. Because even though I can do it here on the video for you, you want to be practicing all this stuff too. So we get an expression like this. 718.24 equals 169 plus 4.4 times x. And many students want to make the mistake of thinking that you can just add these numbers. That would be nice, but we can't do it. What we do instead is we want to isolate x. So we want to get rid of these numbers on this side of the equal sign, the 169 and the 4.4. 4.4 is too close to x, don't do that first. We're going to simply subtract 169 first on both sides of the equation. Take some time to subtract these. And don't just trust me on this. It's late in the day, I might be making mistakes myself. So I'm getting 549.24 equals 4.4x. And we will just divide both sides by 4.4. And I get that x is equal to, this crosses out, 124.8 meters as the distance. Cool. That's it. That's enough to kind of get started on the kinematics assignment for this lesson. And that is all.